digital communications, we're going to focus on UART, SPI, and I2C. When you connect a microcontroller to a sensor, a display, or other module, do you ever think about how these two devices talk to each other? What exactly are they saying and how are they able to understand each other? So we use communication protocols between electronic devices, and both sides need to speak the same language, otherwise things will not work. And these languages are called communication protocols. There are only a few communication protocols we need to actually know when we build this type of embedded systems: UART, SPI, I2C, CAN, USB, and Ethernet. And we're going to focus on UART, SPI, and I2C. And why these three? Well, they're quite a bit slower than protocols like USB or Bluetooth or Wi-Fi, but they are a lot more simple and use less hardware or less resources than the other ones. And they are ideal for communications between microcontrollers and sensors where you have a large amount of high-speed data that they don't need to be transferred. So why are we using USB or Wi-Fi for a small amount of data? Let's see this definition of serial versus parallel communication. Parallel communication, the bits or data are sent all at the same time. So notice that you have a clock, and when I clock the system, all the data is sent in one clock to one end. While if you're doing serial communications, the bits are sent one by one through a single wire. So you have the clock, you still have the clock, a way to synchronize between devices, and then per clock you have a bit. Per each clock you have a bit that you're going to transmit. So it's important to understand the difference between serial and parallel, because communication protocols are going to send information either in parallel or in serial. So let's go over UART. UART stands for Universal Asynchronous Receiver and Transmitter. The main purpose is to transmit and receive serial data. And you find a lot of UART modules, namely, for example, GPS modules or Bluetooth modules or RFID cards. So pretty much, since UART kind of got blended with USB by using the FTDI chips, you see UART everywhere. And you see different types of UARTs. You see the RS-232, the RS-422, and the 486. So what is the difference between these different communication protocols inside of UART? Well, we have a table here that tells you the difference. For example, the maximum cable length that they can handle, the maximum bits per second, the voltages, the loads, the resistance, and all that good stuff. The majority of the times for short distances we use these 232, but as we start going like longer distances, notice here that only handles 20 meters, you start using other protocols that start going to differential to handle noise, and you also have the 485. So how does the UART communication works? So they communicate directly with each other. So you connect the transmission to the receiver of the other device and the transmission side of second device to the receiver side of your first device. This can be sometimes a challenge because it depends on how the manufacturer actually labels on the PCB board the TX and RX. And so if you are building things and you're getting frustrated, things are not communicating, just give it a try and understand if you are not swapping these RX and TX. And maximum wires used are 2. Maximum speed can go up to this baud rate. Now you can go a little bit higher, depends on the device that you're using, but these are the traditional baud rates. It is asynchronous, so there is no clock, and it's a serial, and you only have a master or slave. So you cannot have multiple UARTs connected together. You only have 2 UARTs connected together. The transmitted data, so the package, this is the structure of it. You have a start bit, and then you have the data frame, can go from 5 to 9 bits, and then a parity bit, so an error checking way. So it does not perform error correction, just error detection with the parity bit, a very simple one, and then the stop bit. And you transmit that over the UART. So that means that your receiver and transmitter need to agree on this packet before they start transmitting information. Pros and cons: advantages: only uses 2 wires, no clock signal, as a parity bit for error checking, and the structure of the data pack can be changed as long as both sides are set up for it. It's well documented and widely used method. Disadvantages: the size of your data frame is limited to a maximum of 9 bits, does not support multiple slaves or multiple masters, and the baud rates of each UART must be within 10% of each other. So when you're doing the detection of those bits, when you're sending the transmission, the receiver needs to be like 10% of that transmission rate, otherwise you start not receiving the bits properly. Let's go over the SPI. SPI stands for Serial Peripheral Interface, and it's a common communication protocol used by a lot of different devices such as SD cards, RFID cards, 2.4 GHz wireless transmission receivers, and they use that to communicate with the microprocessor. The communication is done through a master and slave approach, and what you do is the master is controlling the device, usually a microcontroller, while the slave, which is usually a sensor or display, just receives instructions from the master. And the simplest configuration is the single master, single slave. But notice here that what we have the MOSI, and which is the line for the masters to send data to the slave, which means master output, slave input. You have the MISO, master input, slave output. You have the clock, and you have the ship select or the slave select. So if you have multiple slaves, this is the ship select is going to be able to select which slave do you want to transmit information. Some specs: so you're using 4 wires now. Maximum speed, you can go a little bit higher than the UART. You can go 10 megabits per second, depending on how far away the devices are. It's synchronous because you have a clock serial, and the number of masters 1, number of slaves theoretically unlimited, but you are actually able to, you are actually bounded based on the load capacitance of your system. What does that mean? So let's go over configurations. Multiple slaves. So notice here that I have my master that shares the MOSI, MISO, and clock between the 3 slaves, but then I have 3 independent ship selects, so I can select which slave do I want to talk with. If I start adding slaves, the problem is that the impedances of your slaves are going to load the line, and that's what it makes it. It's theoretical possible, but in practical you cannot have that because it starts affecting the integrity of your signal. You also have the daisy chain configuration, where in this case what you do is you pass the MOSI to the MOSI of slave 1, but then you connect in this kind of daisy chain connection the MOSI and the MISO between the slaves, and then the last one closes the loop with the MISO. How SPI works: the master outputs the clock signal, so I start sending a clock, and then I switch the ship select from a low voltage, which activates the slave. So the slave. So I do that switch, and now the slave knows that, okay, I'm ready to receive information. Then you can send the data 1 bit at a time, and it's received by the slave, and then the slave is going to use that clock to either send information or not send. It depends, but it can just receive commands or it can send data back, and it's all the time. Notice here that the least significant bit is sent first, while on your master it's the most significant bit that is sent first. So that's a very important distinguish between both. Pros and cons: there is no start or stop bits, so the data can be streamed continuously. No complicated slave addressing system like I2C. Higher data transfers, normally a little bit higher than I2C, and you have separate transmissions and receiving lines, so data can be sent and received at the same time. Disadvantages: uses 4 wires instead of 2. It does not have any type of acknowledged data or any type of error checking, and only allows for a single master, so you can only have 1 master connected to your system. Let's go over I2C. I2C combines the best features of SPI and UART. With I2C you can connect multiple slaves to a single master, or you can have multiple masters controlling single or multiple slaves. You probably find I2C when you build like OLED displays or barometric pressure sensors or gyroscopes modules, so that's widely used. Like UART only uses two wires, the SDA and the SCL, so the clock and the data. Notice that the data is bidirectional, so you use just the wire to send information and receive information. And it's a serial communication, so we call SDA serial data and the SCL serial clock. Some specs: two wires, maximum speed, a little bit slower than your SPI, but faster than the UART. It's synchronous as a clock. In theory, again, the number of masters can be unlimited. The master of slaves is 1008. That's because of the structure of I2C package. Configuration: so this is the single master multiple slaves. Notice here that they all share the same clock and the same SDA. This is an important feature that we should never forget on I2Cs, is to check these pull-up resistors on the line. Sometimes we forget these and then I2C is not working. They need these on the lines mainly because the output of your master most likely is a high impedance or open drain, open collector, and this is what it's important to make this system work properly. This is the configuration of multi-master, multi-slave, so I can have multiple masters connected to multiple slaves. Same thing here, make sure that you have those pull-ups. And during the protocol, this is possible because during the I2C protocol, they are going to send addresses back and forth. So all these devices have an address name, unique address name. That's why it's possible to do this configuration. This is the I2C message. So you have the start condition, the address frame, acknowledge bits, and then data frames and stop condition. How it works: there are 6 steps involved in the data transmission. Step number 1, the master sends the start condition, and the start condition is by putting the SDA from 0 to 1 before you actually do a 0 to 1 on your clock. Once that happens, the slave knows that, okay, we're going to receive information. Then you send the address. Notice that all of them have addresses, and when I send the address, only the slave that matches the address is going to communicate with the masters. And the cool part is that it sends an acknowledge, which is important. So now the master knows that the slave, in this case number 3, is ready to receive information. The master sends or receives the data frame, so the protocol now goes back and forth, and again slave 3 sends acknowledges back and forth, and then you just terminate your condition by switching the clock high before you actually do your switching the SDA to high. Pros and cons: only uses 2 wires, it's an advantage, supports multiple masters, multiple slaves, it has this acknowledge, hardware is less complicated, and a well-known and widely used protocol. Some disadvantages: the data transfer is slower than SPI, data frames are limited to 8 bits, and more complicated hardware needed to implement than the SPI. So the hardware is less complicated than the UART, but a little bit more complicated than the SPI. Outline: regarding other types of protocols, the USB, CAN, and Ethernet, just highlighting different types of USB standards that you have. We're not going to work with USB for now, and probably this is the fastest USB that you have. USB 3, you probably have the USB 3.1, can go up to 10 gigabits per second. Do not confuse the physical connector. So USB-C is just a physical connector, is not the speed. I can have USB 1.1 implemented physically with a USB-C connector. So this is like as fast as we can go now with USB. And then we have CAN, which is widely used in cars to transmit information between sensors and your microcontroller, or the brain of the system.